Yeah, so today we're starting with 3.5. So just before we look at what valency is and what the valency of an element is, we have to kind of recap the different charges of the different components of an atom. Okay, so obviously we've got our proton. Our proton is a positively charged, okay? That's a positively charged. That's important to know when we talk about cations, okay? Because cations are positively charged, Electrons are negatively charged. And we say neutrons, similar to the word, are neutral. They don't really have a charge, okay? They're not positive, they're not negative. They have no charge in the atom. So when we're talking about, any element, usually in the periodic table, if we talk about carbon, for example, okay? If I can draw a little box like the periodic table. Carbon is obviously chemical symbol C, and it has an atomic number of 6. What that means is that carbon has 6 protons, because that's what atomic number is. Yeah, atomic number is the number of protons. So it's got 6 protons and it's got 6 electrons. Okay, in the periodic table, all the elements have an equal number of protons and electrons. If you know the atomic number of an element, for example, carbon is 6, we know that it's got 6 protons and 6 electrons. We say this because in the periodic table, all of our elements don't have charges. Okay, like I said on Wednesday in our class, it's not called the periodic table of the ions. It's called the periodic table of the elements. And all the elements in our periodic table are written as their specific atoms, not as ions. Okay, and we're going to talk about what the difference between atoms versus ions is in the next slide. Okay, so from this slide, what I really want you guys to understand is that protons are positively charged, electrons are negatively charged, and that in the periodic table, any element has an equal number of protons and an equal number of electrons, okay? But this is only with reference to the atom, okay? When we start talking about ions, like cations and anions, okay, the number of electrons is going to change, or the number of protons is going to change in such a way that either the protons will be more than the electrons or the electrons will be more than the protons. Okay, and we looked at a worked example of this on Wednesday, but we'll go through it again as well today. Now, if you guys have any questions as we're going through these topics, just put them in the chat box and I'll be happy to help you out there. Okay, so when we're talking about ions, okay, on Wednesday, we talked about this idea that in order for an atom to be stable and to feel complete, its outer shell has to be full, okay? Outer shell has to be full means that the outer shell needs to have 8 electrons, okay? That's what we call as a full outer shell. So a full or a stable or a complete outer shell has 8 electrons, okay? For almost all the elements in the periodic table, this is the rule, except for, if anyone remembers, helium, okay? Helium, He, is a noble gas, and it's the only element in the periodic table that is stable with 2 electrons in its outermost shell, because helium's atomic number is 2. It can't go further than that in terms of electrons, okay? So 2, and that's stable. But for any other element, it needs 8 electrons in its outermost shell. So that's our magic number there, okay? 8 electrons need to be present in the outermost shell for that to happen. When we're talking about an ion is basically an atom that has become charged. So either it's an atom that has started to get a positive charge or it started to get a negative charge. So that's basically the 2 types of ions that we look at, okay? So generally when we're looking at ions, we're talking about an ion as having either one of 2 charges there. Okay, so basically when we're looking at, for example, sodium, this was the example I showed you guys on Wednesday. Okay, sodium has 1 electron in its outermost shell. And we said that it's actually easier for sodium to lose that 1 electron and give that to another element that might need it. For example, another element that has 7 electrons in the outermost shell compared to just gaining 7, okay? And that's why we say sodium, because it gives away its electrons and it loses that negative charge, it actually becomes more positively charged. So in other words, if I just kind of get rid of all those scribbles there, in other words, when we look at sodium in the periodic table, it is an atom. And that means that it has no charge, okay? But when sodium starts to combine with other elements and starts to form what we call as bonds, okay, sodium actually becomes positively charged. So you notice the difference between these two is that this doesn't have a charge attached to it, whereas this has a plus charge. Okay, this is a sodium ion. And you'll also notice one difference in that the first sodium atom has 3 electron shells here, but the second example here only has 2. That's because this last 1 electron was lost. And when we lose that electron, we also lose that shell. That whole shell goes, kind of vanishes there. Okay, so that's basically what we talk about when we talk about our atoms versus ions. An ion is simply an atom that has developed a charge, okay, either by losing or gaining an electron. In this case with sodium, sodium has lost the electron, okay? It's lost the electron. This is the confusing part. When you lose an electron, it doesn't mean that it's a negative charge, okay? Although that's sometimes confusing sometimes because you think, okay, well, when you lose something, it's supposed to be negative. It's like subtraction, but that's not how it actually works, okay? When you lose an electron, you're losing a negative component, okay? And when you lose a negative component, you actually become more positive. So if we look at sodium here, for example, sodium has an atomic number of 11. So in a normal sodium atom, you should have 11, I'm going to write 11p for protons and 11 electrons, okay? That's how it should work. That's equal. But in the sodium ion, what happens when this atom actually gives away one of its electrons to another element? We actually notice a pattern coming up here where you've got 11 protons now, but you've only got 10 electrons. So you've got more protons than electrons, more positivity than negativity, and that's why sodium gets a positive charge there. Okay, that's why our cations, regardless of what element we're looking at, our cations are always positively charged because they've given away or they've lost an electron. On the other hand, our anions are always negatively charged because they've gained an electron. Even though gain would suggest plus, in our case, that's not what we say, okay? When you gain an electron, it's like saying that, you know, for example, chlorine, okay? Chlorine has an atomic number of 17. So that would generally mean 17 protons and 17 electrons if we're looking at the chlorine atom, okay? But when chlorine accepts that 1 electron from sodium, what happens is that the chlorine ion, which is actually called chloride, not chlorine anymore, because it's now an ion, not an atom, now has 17 protons, but 18 electrons, because remember, it gained, okay? So because it's got more electrons now, it's actually got more negativity compared to positivity. And that's why we say that anions have a negative charge, because they are more negative because they've got more electrons than positive. Okay, really, really, really important to understand this idea. I know it's something you might have gone through last year as well, but we really need to get this down pat. Okay, so that is the idea. That's how ions are formed, okay, how cations are formed and how anions are formed. Okay, this slide here literally just repeats the previous slide. Just all those examples I was writing down before, this slide kind of tells you what it is, okay? And this second point here just shows you that, again, if you've got 7 electrons in your outermost shell, it is easier for you to just gain 1 electron rather than giving those 7 away to lose the shell. Okay, so you kind of have to use your kind of logic, okay, when it comes to deciding whether an element will be a cation or whether an element will form an anion, okay, whether an element will be that is positively charged or whether it will be negatively charged. So that's the basic idea. The basic rule is that most of our metals form cations and most of our nonmetals form anions. Okay, that's the basic rule there. Okay, so far, how are we going? Like, does anyone have any questions? If you do, just put them in the chat box. There is one question here. Yeah, so the usual order of the shells with the electrons is 2a to 1832, but in our case, what we're looking at is we're just looking at the outer shell. Okay, with the outer shell of most electrons. We could say, oh, why can't we just deal with 32? But the problem is that not all, remember we said that rule only really applies to elements that go past atomic number 20, which is past calcium. Okay, so generally for the lower elements, we just need 8 there. So for elements that are within the first 20. And to be honest, like those are the elements that we really deal with when it comes to electron shell diagrams. The harder ones we did in class were just for you guys to practice. But yeah, that's why we say that we're looking at the 8 electrons in the outermost shell there. Okay, and that's what allows us to see whether an element is stable or not. Okay, so when we're looking at the next thing, this is what I just said before as well. The reason that the reason that our metals form cations is because, as we know, metals in group 1 and group 2, we said metals in group 1 have 1 valence electron, metals in group 2 have 2 valence electrons, okay, which means that group 1 metals have 1 electron in the outermost shell, group 2 metals have 2 electrons in the outermost shell, okay? And because that's such a small number, it is easier for them to lose those electrons than to gain, okay? They have the tendency and the habit to lose electrons, okay? And that's why most of our group 1 and group 2 metals become positively charged and they form those cations. The nonmetals, on the other hand, if you remember when we were looking at nonmetals on Wednesday, you know, when we're talking about our halogens, for example, our halogens have 7 electrons in the outermost shell. Okay, that's a lot. That's a big number. There's no point of it losing those 7 electrons. It's easier for it to just accept an electron from a metal that's donating that electron to it. So rather than losing all 7 and trying to lose the shell, which does require a lot of energy and a lot of time, it's easier for it to be like, okay, I've got 7 electrons and sodium is attempting to donate 1 to me. So let me take that 1 electron from sodium and add it to my number of electrons and get 8 electrons and become stable there. Okay, so that's why anions tend to form, nonmetals like halogens tend to form anions, okay, because they always accept more electrons into them, which makes them more negative, okay? So that's the basic idea there. So that's the basic idea. Now with these 3 here, if you remember from Wednesday, can anyone write in the chat box, what's the name of these 3 elements, or the name of the group that these 3 elements belong to in this picture here at the bottom? If you remember the name of that group. Okay, let's see. Excellent. Yeah, it's noble gases. Okay, so our last group here, if I can go over it like that, yep. These are our noble gases. Okay, so neon, argon, krypton, they're all examples of noble gas. And then we say they're noble because they've got 8 electrons in the outermost shell. 8 electrons in the outermost shell means that they don't need to mix with the common folk. They don't need to go begging for electrons from other elements or from metals. They are non-metals that are noble, they're royal, they don't need to interact with common elements. And for that reason, because they don't have to interact with common elements because they're already like complete and they're basically perfect, they are called unreactive. Okay, they are unreactive because they don't react or interact with other elements because they don't need to, because they have complete and full valence shells. Okay, that means their outermost shell is already full of electrons. It's got 8 electrons, which makes it stable already. Okay, they don't need to go searching for that stability because they've already got that stability. Okay, and for that reason, we actually say that the valency of our noble gas elements is 0. Okay, so we don't add a +1 or -1 to that. And we'll talk about what +1, -1 and everything means in the next slide. Okay, so far, is any part of what we've gone through like confusing? Because this is actually a confusing topic. If there's any part that you find confusing, please just put it in the chat box and I'm happy to go through it again. Okay, now before we move on to the next slide, I just want to bring your attention to the second thing here, the second diagram. So this is showing you a potassium ion. So it's not mentioned here, but our potassium ion has an atomic number of 19. Okay, that means that the potassium atom means uncharged, should have, let me ask you guys this. Okay, in the chat box, tell me how many protons and how many electrons the potassium atom should have. Not the ion, the atom. And then I'll use your answer to write it down, just to see how much you guys remember. Yeah? Okay, so you need to mention how many protons and how many electrons. Let's have a look. Yeah, 19, excellent, good work. So 19 protons and 19 electrons. These numbers are not different because we said the basic rule for all atoms in the periodic table is that they'll have an equal number of protons and equal number of electrons. Yeah, nothing's changed here. If we look at the electronic configuration, 2 + 8 is 10, 10 + 8 is 18, 18 + 1 is 19, which adds up to what the atomic number is. Okay, that's basically neutral, there's no charge yet. Now, what happens when potassium donates its one outermost electron or one valence electron to another element, regardless of what element that is? It could be chloride, could be any of our halogens, okay, in group 17, could be fluorine, could be bromine, anything, okay? The minute that potassium donates that one electron, okay, let me use a different color to highlight that. That one little electron that's all alone in the outermost shell, the minute that it donates that to chlorine or fluorine or any of those group 17 elements there, it actually loses that electron, okay? So if we look at our potassium cation now, can anyone in the chat box write down how many protons and electrons will exist now in the potassium ion or the potassium cation there? Yeah, so we've got, let me have a look at the answers. Yeah, excellent. Yeah, so there'll be 19 protons now. The protons never change. And that's why we answered this question in our first worksheet, guys. Remember, we said, why is the atomic number such a good way of organizing elements? Because when these interactions occur, the number of protons in potassium doesn't change. It stays the same. It's only the number of electrons that change. Okay, so the number of electrons will be 18. So excellent work, guys. Okay, so the number of electrons has decreased. Okay, because the number of electrons has decreased and we've got more protons here, we've got more positivity, we've got more positive charge. That's why the symbol for the ion of potassium is K plus and not K minus. It can't be K minus because there is less electrons in there than there is protons. Okay, I know that's confusing, but it's just like once you do a few examples, you can get your head around it a bit better. Okay, so that's the basic idea of why metals form cations and why nonmetals form anions. Okay, so let me just go to the next slide. Okay, so this is the same thing, just showing you a few more diagrams here of what the whole interaction looks like, okay? When one metal, for example, donates or loses or gives away one of its outermost electrons to a nonmetal. So you can see in the first example here, and this is the example we went through in class as well on Wednesday, sodium and chloride. We know sodium chloride is salt, okay? That's just the table salt. Okay, we know that sodium chloride is just salt. So basically what that means is, who is not muted? Let me go mute them. Okay. Okay, so sodium by itself as a group 1 metal is very reactive, it's very dangerous. But, and chlorine by itself is also very dangerous, okay? But when we combine these two, sodium and chloride together, basically what that means is that they form a compound that's not actually that dangerous, okay? Which is sodium chloride. So sodium by itself has 11 protons and 11 electrons, and chlorine has 17 protons and 17 electrons. All right, so when sodium donates that one outermost electron, which we can see here, to chlorine, we can see chlorine actually gets more electrons in that process, which means it becomes more negative, which is why chlorine's ionic symbol is Cl minus. Sodium actually loses that electrons, and now it's only got 10 electrons, which means it's more negative, okay? Which means it's more positive now because it's got more protons. So that's why we've got Na, and we don't put a minus there, we put a plus because it's got more protons than electrons, which means it's more positive than it is negative. Okay, so that's what we call as ionic bonding. And we're going to learn about what ionic bonding is. Okay, ionic bonding in very, very simple terms is when a metal such as sodium combines and interacts with a nonmetal such as chlorine. Okay, and that basically forms an ionic bond or an ionic compound. The compound that's formed when sodium Na and chlorine Cl form together is called sodium chloride, and the symbol for that is NaCl. NaCl or sodium chloride is an example of an ionic compound that's formed through an ionic bond or an ionic relationship. Okay, and an ionic bond is simply a relationship or interaction that involves a metal and a non-metal, okay? usually where a metal will either donate its one electron or consequently or similarly where a nonmetal will accept an electron or gain an electron there. Okay, I think there was a little GIF on this slide here. If I can go back and come back. Yeah, you can see in this GIF here how the electron can go to the other one there. Okay, the same thing with potassium here, which is just the example we looked at before. Just important for you guys to see how this transfer occurs. Okay. Alrighty, so looking at the periodic table, now I want everyone to open their books to page number, what page was it? Let me have a look. Page number 70 something, I think it was. The page where your periodic table is. Page 71. Okay, so go to page 71 in your book. And I just want you guys to write down some of the common charges or valencies of specific groups, okay? We can't put a charge for every group in the periodic table because remember when we were first doing metals, we talked about the fact that some of the metals, particularly our transition metals, don't have set charges. We said that they are variable in terms of their charge, okay? So I just want to explain some of those charges and get you guys to write that down in your book so you have that with you, okay? You'll always get the valency table in the test, okay? You'll always be allowed to bring in the valency table and periodic table. We'll give those to you, but it's important to memorize the valencies or charges of some of the common ones like sodium, lithium, chlorine, those kinds of ones, okay? So the first one is group 1 metals. We know that they've got one valence electron in their outermost shell. Okay, we know that they lose that electron, okay? So we saw that example of how sodium always loses the electron. Because it's got one valence electron, which it loses to become more positively charged and to form a cation, I want you to write +1 right next to group 1, okay? That means all the elements in this group 1 have a +1 charge, okay? So that's basically what it means. So if I was to write any of these, if I was to write the chemical symbols for the ions of any of the elements in group 1, I'd write okay, H+, Li+, Na+, okay, and you guys get the idea, okay, K+, it's the same thing. So any of the elements in the group 1 of the periodic table have a +1 charge. Now you might be asking, hey, why are we only writing plus? Why can't we write +1? Well, it's the same concept as in maths, okay? In maths, when you're writing X and Y, you don't write X1, you don't write Y1, but you assume and you know that. Give me 1 second. Okay, you assume and you know that, those elements will be having a +1 charge there, okay? We don't have to write H +1. We know that plus means +1 in the same way that we know that X means X1, okay? So that's basically that idea there. Someone's done a nice little scribble on my slide. Okay, so the same thing goes with, so this is +1. Same concept for the second group. We've got, this is going to be +2. Okay, the reasoning behind that is that +2 means that all of these elements or all of these group 2 alkaline earth metals have 2 electrons in their outermost shell, and they lose those 2 electrons. And when they lose those 2 electrons, they will become more positive than negative, because now they've got less electrons in them. And the same thing goes when we write the ionic symbols, we would write Be2+, okay, or we would write Mg2+, Ca2+, Sr2+, Ba2+, Ra2+. So we write the 2+ here, okay? That is basically suggesting that beryllium here forms a cation, a positively charged ion with a number, with a 2 charge there, okay, a +2 charge, which means that it's lost 2 electrons to become more positively charged. So that's basically that example for group 2. So the first one should be +1, second one should be +2. Now, our transition metals, let's see if you guys remember, our transition metals don't have, we can't do the same thing. We can't just say, okay, everything in fact, I'll ask you guys a question. Hold on. Is this correct? Write in the chat box whether or not this is correct, and then give me a reasoning as to why it might be correct or why it might not be incorrect, what I'm doing here. Okay, we've got some answers. Let's see. Okay, yeah, it's not correct. Can anyone give me the reason as to why that's not correct? We talked about this when we did the types of metals. And I think I mentioned it just before. Yeah, because these electrons really depend on the specific element that we're looking at, okay? With the transition metals, which are the light blue ones here, we can't really put a set charge because the charges or the valencies on these are variable. For this reason, in a test situation, not just in year 10, but even at a VCE level, if we were to give you, for example, let's choose one, iron, okay? If we were to give you iron, usually we would give this to you with a Roman numeral inside like this. And this is why it's important to know your Roman numerals. Fe, and that's the Roman numeral for 3. And that tells you that in that specific example, iron has a 3+ charge, okay? Copper, for example, copper is often written like this, Cu and then a 2, okay? That means that in this example, copper has a 2+ charge. So you can see that in the transition metals, there's no set charges. We can't just go down the column and say, okay, all of these will have a 2+, all of these will have a 1+ charge, okay? They're variable, okay? They don't have a set charge. Okay, so that's the transition metals done. So we don't need to memorize, or we don't need to know that, okay, all of these have the same charge, because they don't, okay? They're variable and they will differ depending on the situation. In most cases, you have an idea of what the charge is by looking at the Roman numeral indicated in the brackets, okay? And a lot of the transition metal charges, because they are unknown, they're usually on your valency table as well in your data booklet. Okay, so let me just clear all that mess. Now we'll go to the nonmetals, and I'll just tell you guys some of the valencies of the nonmetal, or some of the charges of our nonmetal groups there. Obviously, can anyone guess what kind of charge the noble gases would have? Group 18. Considering that they don't interact with common elements, they don't gain electrons, they don't lose electrons, they just stay as they are. Can anyone give me a number that corresponds to the charge that you think a noble gas would have? Yeah, they're neutrally charged. Because they're neutrally charged, we say they have a valency of 0. Okay, so they don't have a valency, they don't have a specific charge there. Excellent. Okay, with our halogens, we know that the halogens have 7 electrons in the outermost shell. Okay, fluorine, chlorine, bromine, all of those. They've got 7 electrons in the outermost shell, the ones in purple here. So obviously that means that they actually gain an electron from a metal to make a full 8 complete valence shell of 8 electrons. For this reason, we say that they become more negatively charged because they gain 1 electron. Okay, so that charge will be -1. The valency for our halogens is -1. The valency for our this group of nonmetals here, which we haven't looked at in depth, but they are still considered our nonmetals, is, oxygen, sulfur, selenium, all of these ones we would say is -2. Okay, so that's basically our valency for that group there. And for nitrogen, phosphorus, we say it's -3. So all this means, guys, is that these elements gain 3 electrons from a metal in most cases to actually make a anion with a -3 charge. Okay, this means the number means that they gain 2 electrons to make an anion with a negative charge, and this means that they gain 1 electron to make an anion with a negative charge. Okay, so that's the basic idea, guys. Yeah.
Miss.
Yeah.
The class ended 7 minutes ago.
Class ended. No, our class is going up to 12:50 today.
Oh, why?
Oh, because we started, we had the quiz as well. And I didn't count the period 3 as being, I was going to make period 3 online as well, but then I thought I'd just take an extra 10 minutes of this.
Okay, got it.
Yeah, unless you guys want to have a double period online session, I'm happy to do that.
No, I'm good.
Okay. All right, so guys, just 2 more minutes and then we'll wrap it up. All right, so yeah, that's the charges basically. Okay, so we're looking at the charges of the thing. So you guys should have written that down because we will be referring back to that, okay, as we go through the rest of this. So inshallah, we'll finish the rest of this on Monday. And the first thing we're going to do on Monday is learn how to write these chemical formulas. So make sure on Monday you bring your periodic table with you. so we can, go through this activity together. Okay, cool. So that's basically all we're going to do for today. If you have any questions, let me know. You can start your 3.5 worksheet for those of you who want to get ahead and not fall behind. So in the 3.5 worksheet, I don't want you to do all questions. I just want you to do questions. Let me just see. Questions 1 to 1 to 7. Okay, so guys, just do questions 1 to 7 from your 3.5 worksheet. Okay, that's it for today. All right, I'll see you guys on Monday for our next live session, inshallah. Okay, bye-bye.
Bye, miss.
Bye.